Hello everyone, my name is Maisha Anjum and my presentation topic is effect of artifact removal on EEG-based motor imagery PCI applications. This is the outline of my presentation. What is motor imagery? Motor imagery is the imagination of limb movement. During motor imagery, characteristic brain signals are generated from the motor cortex region of the brain. These brain signals can be detected using the EEG method, which is non-invasive, low-cost, and has high temporal resolution. The most prominent frequency range of the EEG during MI is from 8 Hz to 30 Hz. However, this EEG signal can be used as command signals, can be further processed and used as command signals for operating an electrical device in brain-computer interface. However, EEG signals are susceptible to artifacts, and these artifacts are mainly due to power line interference, biomedical signals like ECG, EOG, eye movement, etc. Artifacts in EEG can result in false positive output commands for the electrical device. Therefore, artifacts in EEG are detrimental to the performance of the system. After doing literature review, the major problems that were discovered is that only one type of artifact is targeted to be removed. The performance of the artifact removed is not usually quantified. Also, the artifact removal method is proposed for general application rather for a particular application in most cases. Therefore, the objective of my research study is that to identify a suitable artifact removal method, then apply it on a new MI dataset designed by us, and then study the effect of artifact removal from signal for MI BCI classification. More than 5 papers have been reviewed for literature. Among them, 2 papers are mentioned over here for which we have a significant difference with our work. In the first paper, the limitation predicted was that the artifact removal method is proposed for only general application, not for a particular BCI application, and it is also semi-automatic and semi-supervised. So the user has to manually operate some parts of some of the steps of this artifact removal method. In our study, the artifact removal method used is applicable for online application. The user only has to set a threshold to detect threshold to detect the artifactual segments, EEG segments, depending on the BCI application. In the second paper, the limitation is that the method is not applicable for single channel EEG, and also one type of artifact removal has been targeted. The artifact removal method used in our study is that it's only applicable for single EEG signal. It's also applicable for single channel EEG signal, and it targets all types of artifacts. This is the research methodology opted for the research for the study. First, the literature is reviewed to find the problem. Then a new MI dataset is acquired by designing an experiment. Suitable artifact removal method is then applied, and further the MI features are expected, passed on to artificial neural network classifier, and finally the performance is evaluated. The theory behind the selected artifact removal method is that it uses stationary wavelet transform for analysis, which is suitable for non-stationary signals. The higher wavelet transform is chosen for lower computational complexity. The design of the artifact removal method is that the EEG signal is divided into 1 second segments. Afterwards, the stationary wavelet transform is applied, and the artifactual segments are detected by calculating the probability using the kurtosis, skewness, entropy, and periodic waveform index waveform index values. Then, depending on the threshold set by the user, the algorithm automatically detects the probability of the segment being artifactual or not. If it's artifactual, then the segment is opted out of then the segment is deleted from the. Then the segment is not included for further inverse stationary wavelet transform, and only the segments which are non-artifactual are further processed with inverse stationary wavelet transform to gain the same EMG signal. This is a picture of the subject performing motor imagery during our designed motor imagery experiment. The experiment was divided into two sessions where the subject imagined right-hand movement and left-hand movement. The subject wore a 14-channel EMG headset which had a sampling rate of only 128 Hz. The data of 11 subjects have been used, and finally the alpha, beta, and theta power were used as the features for the classifier. Here we can see that the artifact. We can see the figure of the EEG signal for a single channel before and after artifact removal. Here there are spikes due to artifact. This orange signal is the EEG with artifact, and after artifact removal, the spikes has been removed. And this is the blue signal is the EEG signal after artifact removal. The highest SNR calculated is for the second subject, where the SNR has increased by 12 dB, and the overall accuracy increased by 8%. The summary is that there is significant improvement after artifact removal because of applying the artifact removal method. Also, the number of subjects, however, the limitations is that the number of subjects participating for data collection is low, and due to limited sampling rate, only 128 Hz, gamma band power could not be used for feature classification. Future works decided are that more performance evaluation criteria is to be detected. Also, different types of criteria is to be calculated. Also, different types of classifiers like SPM, KNN is planned to be applied. And artifact removal method is also planned to be applied for other kinds of BCI applications like XSB. These are the references and used for this presentation. And I would like to thank my co-authors and my supervisor for helping me out with this study. Thank you everyone for listening to me.